Hello, and welcome to part 7 of my NES Emulator series. If you've made it this far, a big thanks to you for sticking with it for so long. This video is about the mappers, specifically the mappers you're going to need to use to implement the bulk of the Nintendo catalogue of games. But whilst I was planning this video, something dawned on me. It's very difficult to make a video about mappers. And consequently, this video is presented in a different style to how I would usually make videos. Normally I like to build up the project line by line and show you it working at various stages and provide small tests and explanations of what's going on. The problem is, mappers don't work that way. They either work or they don't, and they need to exist in their entirety before you even know if they work or not. And this makes them especially difficult to debug. And so instead, what I'm going to do is present a review of the mappers that I've made already for this project. They're the main mappers you need for most of the Nintendo games. And I'll walk you through how to understand the mapper specification and how to translate that into code. I also expect that given that this is part 7, and if you have made it this far, you're probably already quite familiar with the NES architecture by now, and so perhaps I don't need to go into quite as much detail as I have done at the start of the series.
So let's get started with a quick refresher on what it is the mapper actually does. Fundamentally, it's a device that translates addresses from a CPU or the PPU into memory stored on the cartridge itself, such as the program ROM memory and the character ROM memory. As we'll see later in this video, some mappers have additional capabilities, but for now let's assume they're just doing this simple address translation. Recall that certain locations in the CPU address space and the PPU address space are expected to serve specific purposes. The CPU can address 64 kilobytes, but there certainly isn't 64 kilobytes of memory on the Nintendo console. And when the CPU writes to addresses that doesn't have a physical hardware implementation, it gets mirrored back to some lower number address. We've covered all of this in great detail. We also looked at where the programs start in the CPU address space, and it's about halfway. This means there's about 32 kilobytes of addressable program memory at any given time. So let's just look at a few example configurations. Let's assume that our entire program ROM on the cartridge is in fact only 8 kilobytes. It's a small and simple game. One way to approach this is to map this entire 8 kilobyte memory into the first 8 kilobytes of our CPU address space after the halfway point. And any reads to addresses beyond the 8 kilobytes are simply mirrored in the rest of that space. Hopefully it's obvious that if we had a 16 kilobyte program ROM, we could map that twice into the CPU's addressable space. And if it was 32 kilobytes, well then it's a perfect fit. The mapping is a one-to-one. But let's take things to extremes for a moment. Let's assume our program ROM is 128 kilobytes. Clearly, this can't fit into the 32 kilobyte addressable space. Instead, we must break this 128 kilobytes into 4 32 kilobyte regions, and the mapper will perform that translation for us, depending on which bank we have selected. So these dotted green lines broadly can be considered bank dividers. At some point, the mapper is instructed which bank of program ROM is required to map into the location of the CPU's address space. And in this video, we'll look at the implementation details for some of the more common mappers, as they all approach this in slightly different ways. This simplification that I've illustrated is a little unrealistic. It suffers from one big problem, and that is swapping the entire address space in one go is, well, a bad idea. And this is because as the program is running, there's a great deal of risk in just swapping the memory out, as the program counter will start in the exact same location in the new bank of memory. Now, unless you've carefully coordinated that to be legitimate, that's really just going to make your life as a developer quite complicated. So instead there is a different solution. It's convenient to think of program ROM in 16 kilobyte chunks, and equally think of the program memory's location in the CPU address space also in 16 kilobyte chunks. The mapper may have been configured that all of the addresses in this range are mapped into a specific bank in the program memory, but also that the addresses in this range are mapped to some other bank. This means that when the program counter is operating in this range, it can configure the mapper to change the bank referenced in this range without corrupting the program. And of course, if the program counter is in this range, it can configure the bank mapped into this range. This keeps things a lot more organised for the programmer. The numbers I've chosen here are somewhat arbitrary, and we'll see that the different mappers handle things in different ways. The address space of the PPU is mapped in a pretty much identical way. The address space is, of course, smaller. It only goes to 3FFF, the first half of which is used to store the sprite patterns, ultimately the tiles that make up the graphics we see on the screen, and these tiles are called characters, and thus this region gets mapped onto the character ROM. The character ROM can be partitioned in many ways, just as the program ROM was, and different regions of the pattern tables can be mapped onto different banks of the character ROM. Typically these regions are considerably smaller, because as we've seen in previous videos, if you wanted to animate a particular tile set, you only want to swap in maybe a couple of rows of the pattern table, and it's possible there are several mappings in place at any one time. The mapping for the PPU is a lot more flexible than the CPU because we don't have a program counter to worry about. In the purest sense, it really is just mapping one memory address to a memory address somewhere on the cartridge. So that's what the mapper does, but how does it do it? As discussed, most of the addresses on the CPU bus have a purpose. But one thing we've not seen is any particular register mapped here that could potentially talk to a mapper. For example, to talk to the PPU, we wrote to specific addresses in the CPU address space, and that caused the PPU to change its state. There isn't an equivalent for configuring the mappers. Instead, the mappers take advantage of the fact that the program memory is a ROM. By definition, it's read-only. We can write to these locations, but nothing happens. It's read-only memory. It doesn't change the state of our program. The CPU bus is unaware what read-only memory means, so it can quite happily write to a location here. The mapper will receive this address and the data, but the data simply has nowhere to go. It can't be written to the read-only memory. Therefore, if the mapper detects an address which is in this addressable range where the program is expected to be read from, it can interpret that address as a command to the mapper itself. And it's through this mechanism that we can configure the mapper to set up the mappings between the program ROM on the cartridge and the CPU address space, and the character ROM on the cartridge and the PPU address space. And even though these are two distinct systems, there is only one mapper controlling them both. Now, as I mentioned at the start of the video, I'm not going to be coding up the mappers line by line. Instead, we're sort of going to review how I've implemented a certain number of mappers. And since one of the earliest episodes of the series, we've had a mapper base class, which handles read and write to the CPU bus, read and write to the PPU bus, and over time it's evolved to have a few more functions, and we'll look at these as we develop the rest of this video. In the cartridge CPP file, where we load the ROM image itself, we determine the mapper ID according to the iNES header format. One of those header entries is how many banks of program ROM are there, and it assumes that a bank of program ROM is 16 kilobytes. That doesn't necessarily mean the mapper will interpret it as 16 kilobytes, that's just for us to load it into, in this case, this vector v program memory. And in exactly the same way, we also created a vector for the character memory, and it assumes that there are 8 kilobyte chunks in that instance. Some of the mappers rely on knowing how many program banks and character banks there are. So this information is passed along into the constructor of the mapper, and we'll choose the appropriate derived mapper based on the mapper ID. And for my emulator, I've chosen these mappers because these will cover the bulk of the games, and there's one sort of curiosity mapper. Although I'm not going to do them in this order. Instead, I'm going to do them in order of complexity. The mapper we've been working with throughout this series so far is Mapper 0. And as we have throughout this series, it's time to defer to the great NES Dev Wiki. So again, a big thanks to the guys that have put this together. Under the topic mapper, we really see what the community has come together to form a standard for all of the mappers. And you can see there's a whole bunch of them. In fact, there's another table worth down here. The bulk of the Nintendo games that are most popular in the West are covered by, say, the first half of this table. And in fact, really, the bulk of the games is covered by the first 5 or 6 mappers. I called mine Mapper 0 because it is the 0th entry in this table. So let's have a look at that. The nice thing about Mapper 0, and the reason we've chosen to do it first, is it doesn't really do anything at all. It is not a complicated mapper. But when you're looking at a mapper for the first time, it's often worth seeing which games are compatible with this mapper. And you can do that by looking at this NES Cart DB, another fantastic resource created by the community. So here I've listed all of the Mapper 0 compatible games. And as you'd expected, they're the earlier generation games. But they include titles we've been working with, such as Donkey Kong. In fact, if I click on Donkey Kong, we can see here NES Mapper 0, and it gives us information about the ROMs inside. Here we've got the program ROM and the character ROM. And so by implementing Mapper 0, we can see we're going to cover about 248 of the released titles. Now this also includes all of the slightly more obscure Japanese titles that weren't available to the rest of us. But most importantly, for those that are developing emulators, your usual first goal is to get Mario Brothers up and running. And Super Mario Brothers indeed uses Mapper 0. Now, I'm going to spend a little bit of time on this first mapper just looking at how to digest the information provided by the wiki. The first thing you'll notice is there's lots of peripheral cases. Even though this is Mapper 0, it starts bombarding us with lots of different types of board information, and these are all ever so slight variants of Mapper 0. Because I'm trying to keep this series as simple and as accessible as I possibly can, I'm not going to look at all of the specific details of every possible mapper variation. And fortunately, you don't have to get the bulk of your games working. All of the mappers have this little table at the top. And the important entries here are the program ROM capacity and window, and character ROM capacity and window. And what this is telling us is that this particular board came with either a 16 kilobyte ROM or a 32 kilobyte ROM for program memory. It says for the program ROM window, well, that's not applicable. And this is Mapper 0, it is the simplest mapper. This means there is no mapping. At the start of the slides I showed a 16K or 32K ROM being put into the program memory, and that is exactly what we've got here. It then suggests that there's 8 kilobytes of character ROM, and again, there is no applicable windowing. Windowing is the technical term for mapping. There are a few other tidbits of information on here too. Recall that our name tables are mirrored in a particular configuration, and on Mapper 0 games this is fixed in hardware. Physically, the pins are soldered in a configuration that decides whether it's a horizontal or vertical mapping. There's other bits of information on here too, and we'll look at those as the mappers get more sophisticated. And again, Mapper 0 is the simplest mapper, and the wiki even highlights this for us. How do we interact with it? Well, we can't. This has normally no mapping capability whatsoever. So let's have a look at our Mapper 0. Well, it's a derived class that inherits from the Mapper base class, and it must provide implementations for the read and write to the appropriate buses. Don't forget, there's no way to configure this mapper, it really is very simple, and its behaviour can be inferred by how many program ROM banks were supplied by the cartridge. Here, when the CPU attempts to read from the address bus in the program memory range, if the cartridge only provided a 16 kilobyte ROM, then we mirror the address, effectively splitting the 32 kilobyte range into two identical 16 kilobyte program memories. If, however, we had two banks of program memory, remember each one is 16 kilobytes, so a total of 32 kilobytes of program memory, well then that maps directly into the CPU addressable range where it expects the programs to reside. For the PPU read and write, well, there's nothing to do at all. We just directly pass the address through. These functions take in an input address on the respective bus of the device that's calling them, and they return a mapped address. That's the corresponding address in the entirety of the ROM supplied on the cartridge. So when CPU read is called, the mapper turns that address on the CPU bus into a physical address into the ROM on the cartridge, and this physical address is then used to locate the required data in the program memory vector we created of that ROM. We'll come back to this bit later. The same applies for the write. The same applies for the PPU read and write. So these functions in our mappers simply translate the local space address bus for the CPU and the PPU into the address space of the larger ROM data vectors. I decided to make my mapper implementation also responsible for other bits of information that the cartridge would usually supply, such as the current mirroring mode. The PPU in particular cares about the mirroring mode and needs to interrogate the cartridge to see what it is. And so I've provided this mirror function which interrogates the mapper to determine the mirror mode. But the mapper might not always know what the mirror mode is, particularly in some simple mapper like Mapper 0. The mirroring mode is specified in hardware. If this is the case, we simply return the mirroring mode that was defined in the iNES file format header. If the mirroring mode is not fixed, it is indeed software programmable perhaps, as is the case in some of the more advanced mappers, then we'll defer to the mapper to return what the mirroring mode currently is. I also included a reset function for the cartridge, which resets the mapper. This doesn't set the contents of any of the ROMs, but it does reset the mapper to a known state, and as we'll see, not all of the mappers just get everything set to 0. Now you might think that the next mapper to look at is Mapper 1, but we're going to jump over that one for a minute, straight into Mapper 2. Mapper 2 is great because it's a very simple mapper to implement, but it is responsible for the mapping of some really cool games. And again, according to the wiki, there's 155 games in total that use this mapper. Let's just interrogate the table to get some information. Firstly, we can see that it can have quite a large program ROM. Now, program ROMs aren't just the executable code, they can also be all of the level data and sometimes graphical positioning data that make up the game. Therefore, as the game becomes more detailed and rich and complex, we would expect it to require more program ROM. We know that in the CPU addressable space, we have a total of 32 kilobytes of addressable program memory at any one time, and this suggests we have 16 kilobytes, which is flexible, that can be mapped into any location within the ROM, but also 16 kilobytes that's fixed, so this will always be mapped to a specific location in the ROM. This is quite a useful utility to have, because you could leave all of your system critical functions and startup code in this fixed region that never changes, it's never mapped out, and, for example, load in specific level data one bank at a time, perhaps representing each level. That's probably not how it's done, but conceptually it could be, as and when it's needed. Like with Mapper 0, there is no facility for mapping the character ROM. The 8 kilobytes supplied in the ROM is directly mapped into the pattern tables of the PPU address bus. Mapper 2 allows the program memory configuration to be set up in the following way. The program ROM can be very large, it can be a few megabytes even, all split up into 16 kilobyte banks. Regardless of how large this ROM is, the very last 16 kilobyte bank is always mapped to the top 16 kilobytes of the 32 kilobyte program address space. This is always the case. The lower 16 kilobytes of the program memory can be mapped to any other bank in the program ROM, and so the mapper needs to be instructed which bank is mapped into that space. This introduces the concept of the mapper having registers, and we'll see that more sophisticated mappers have more registers, but this very simple mapper just has the one, and we can write to this register by writing to anywhere in the 32 kilobyte program memory address space of the CPU address bus. And effectively it's telling us that whatever the 8-bit data value is that we write to anywhere within that range, that value corresponds to the particular bank number that we're interested in. And so here's my implementation of Mapper 2. Again, it just implements the interface of the base class, but it has two internal registers. And these are going to be the offsets in banks to the program ROM on the cartridge. We'll start by looking at the CPU write function, because this can be used to program the mapper. As you can see, we're sensitive to any address in the upper 32 kilobytes. And all we're going to do is take the bottom 4 bits of the data and assign that to the bank select low variable. In this case, bank select low refers to whichever 16 kilobyte bank is in this first half of the address space, and bank select high refers to whatever is in the upper half of this address space, though we know that that's always going to be fixed to the last bank in the ROM. The PPU read and write functions don't do anything. This mapper cannot handle the character ROM. When we call the reset function, which we always do when we load a cartridge for the first time, by default the lower bank is set to bank 0. And here you can see where we've passed in the number of banks that the cartridge contains, we're setting the bank select high variable to the last bank of that range. This means when CPU read is called, we can determine which half of the address space we're looking at, whether it's low or high, and then compute the relevant address in the ROM. Given our bank number, we can multiply it by 16 kilobytes and add into that the offset of the address that we actually require. This returns a single number, which is a direct index into the large program ROM vector that was loaded when the cartridge object was created. I do exactly the same for the upper 32 kilobytes, but this is always fixed to wherever this bank is located. Mapper 3 is in many ways the same as Mapper 2, but also the direct opposite, so it's a complete paradox. Whereas Mapper 2 had a window for the program ROM, Mapper 3 has a window for the character ROM. So this would be for very graphically intensive games, but they could be quite programmatically simple games. We can see that either there is a 16K or 32K ROM capability, so this is going to behave exactly the same way as Mapper 0. But there's potential to have 32 kilobytes of character ROM. In this instance, the entire pattern table is mapped at any one time. We'll see in the next two mappers that you can selectively choose regions of the pattern table to be mapped, so you can animate things and mix and match graphics when you're compositing the scene. I'm not going to go into any further detail on this mapper because it behaves in exactly the same way, except it's just for character ROM rather than program ROM. And here is my Mapper 3 implementation. We can see that this behaves exactly the same way as Mapper 0, though it's coded a little differently. CPU write is sensitive to anything within the program memory space, and writing to that, the data value is used to determine which bank of character ROM we're going to use, and therefore in the PPU read function, we use that bank, multiply it by an 8 kilobyte offset, and add the address accordingly, to give us the final mapped address into our vector of character ROM. Nice and simple. Rather oddly, I'm going to jump to Mapper 66 now. Mapper 66 is a very simple mapper too, and I was interested in it because it's the Super Mario Bros. And Duck Hunt combination cartridge. And this is a simple brute force mapper. We can see the ROM can have up to 128 kilobytes, and we can only select 32 kilobytes of that at a time. In effect, we load the entire program in one go, from one of 4 locations. The same philosophy is applied to the character ROM. We can have potentially 32 kilobytes of it, but at any one time we're going to map 8 kilobytes of character data. And this format makes sense when you had multiple games on one cartridge. For example, let's assume all of Duck Hunt is contained within 32 kilobytes, and all of Super Mario Bros. Is contained within another 32 kilobytes, and correspondingly they both have all of their graphics stored within these 8 kilobyte blocks. Then you can easily change essentially the entire game between them. You might use another block to give you a loading menu or startup screen. Interacting with this mapper is essentially a fusion of the two previous mappers we've looked at. We're sensitive to the entire program address range, and we look at the bottom 2 bits of the nibbles of the data that we provide to tell us which character ROM and which program ROM bank we need for the entire range. And this is my Mapper 66 implementation, so I have 2 variables which tell us which bank specifically of character ROM and program ROM we want. When we write to the address bus in the right location, we can extract those numbers directly as being the bottom 2 bits of the data word, and I'll use those values in PPU read and CPU read accordingly. Specifically for Mapper 66, you had to work in 32 kilobyte chunks for program memory and 8 kilobyte chunks for character memory. It's quite a brute force mapper, this one, but useful if you're bundling multiple games into one cartridge.
Well, now we've got the easier mappers out of the way. They are simple translations from one number to another number. But there are 2 mappers which are slightly different from all of the others, and it's just unfortunate that these 2 mappers make up the bulk of the catalogue of the games. This is MMC1 and MMC3.
Mapper 1, formerly known as MMC1, is on the surface quite a complex mapper. Just by looking at the amount of data on the Wikipedia article could put you off. But internally it's actually quite a simple mapper. It just has a rather obscure interface, which I think makes it unique amongst the mappers. However, it's important to get MMC1 working correctly because it covers over half of the released Nintendo games. Examining the structure of the mapper, we can see that it's effectively split into 2. The program ROM banks can be, as we saw before, split into 2 16 kilobyte chunks, where one resides at a fixed location in the ROM and the other is flexible, or it can be an entire 32 kilobyte chunk. And likewise, the same applies to the character ROM. We can have an entire 8 kilobyte ROM bank selected at one time, or we can split it into two, meaning each pattern table left and right can be mapped to an individual 4 kilobyte bank. We also have some additional features with this mapper. We have the ability to have program RAM, so in effect we can enhance the amount of RAM that the Nintendo has in order to perform its calculations or store data. And if there was some battery backup on the cartridge, this RAM could be used to save games. Also, this is the first mapper we've encountered where the mirroring is flexible, a necessary feature for games that can scroll in multiple directions depending on the context of the game. What makes this mapper rather unusual is you communicate with it serially, i.e. just one bit at a time. I imagine this was to reduce the complexity of the chip and therefore reduce the cost, back in the days when producing these sort of materials was very expensive. At the top level, Mapper 1 consists of 2 registers, and as with the other mappers, when the CPU writes to an address above 8000, the mapper is interested in it. If at any point the data that's being written by the CPU has the 8th bit set, then the mapper is reset. However, in all other circumstances, the mapper is only interested in the bottom bit of the data word being written to the address bus. It takes 5 writes to anywhere within this range, and serially shifting in just the bottom bit of the data to populate the load register. And so for each write, we shift in the bit and move it along to give us a more conventional digital word. But if at any point the data word has its most significant bit set, then the mapper gets reset too. And my apologies, a quick little errata, I'm not going to call that the control register, I'm going to call that the target register. Once the load register has been populated with 5 bits, something is going to happen. But what that something is depends on which address was used by the CPU when that 5th bit was written. By only looking at the CPU address, bits 13 and 14, we can break this instruction region into 4 subregions. And so when the 5th bit has been loaded serially, and in combination with the address zone that's being used for the writes, we can target one of 4 functional registers within the mapper. And we can set the contents of that register to whatever the 5-bit data has been loaded in. In this first region, we have the control register, which is used to set various status bits on the mapper, and also the mirroring mode. The next 2 zones are used to set information for the mapper to map the character ROM, and the final zone is used to configure the mapper for the program ROM. These 3 registers will go and perform their function when they're written to, and they each use information from the control register and information from the data that's been sequentially loaded in. There isn't a fixed pattern to this relationship, but it's not complicated. The real complexity of this mapper is this serial loading. Once we've got the relevant data into the mapper, performing the mappings is quite trivial. Here is my Mapper 1 implementation. So for the header file, you'll notice I've now overridden the mirror function. That's because the mapper can determine what the mirroring mode is. But there's also more structural information inside the mapper. Firstly, we have the load register. This is the register that is receiving the bits sequentially, and we need to keep a count of how many bits have been loaded in, because when it gets to 5 we want to do something. And one of those things we can do is write to the control register. And the control register contains all sorts of bits that configure how the mapper works. We've also got the potential to have RAM now on this cartridge, so I'm adding in an additional vector to store this static RAM. Potentially, if we were to implement save states, you'd want to dump this RAM to a file, because it effectively could contain the game saves. The only other variables left are similar to what we've had in previous mappers, but don't forget we now have 2 distinct modes for the character and program memories. Either we're working in big chunky bank switches. For character banks that was 8 kilobytes, and for programs that was 32 kilobytes, so swapping in the whole thing in one go. Or we're working with these smaller resolution bank switches of 4 kilobytes each for the character and 16 kilobytes each for the program. And for the program memory, one of these was always at a fixed location. So I'll start by looking at the reset function. It does reset the mapper to a known state, and the control register is given a specific value. And we'll look at what those bits mean as we go through the implementation. All of the bank selection pointers are effectively set to 0, except for this program bank 16 kilobyte high. As before in a previous mapper, this is set to the last available bank provided by the cartridge. Starting with CPU read, this is the first time we've seen the mapper be responsible for data that's not above the midway point of the addressable range of the CPU bus. And it simply takes the address offset into that range and maps it directly into the static RAM provided on the cartridge. Now, I've hacked in something here to make sure that I don't then go on to affect data elsewhere in the system. If I return a mapped address specifically of all ones, in the cartridge class that has called this function on our mapper, it is sensitive to that one particular condition. This makes the rather naive assumption that we're never going to have a NES ROM with, 4 billion bytes of information. Effectively, what this is doing is saying, well, the cartridge has actually provided access to that memory. So don't go on to read it from elsewhere, because the 6000 to 8000 range is typically valid. It's considered RAM. But I want that RAM to exist on the cartridge and not elsewhere. This is probably slightly incorrect and maybe overkill, but it's working for me. So handling the static RAM is quite trivial, and there is an analogous form for the CPU write too. Sticking with CPU read for the moment, we'll look at how we configure the mapper in a short while. But what we can see is the implementation is quite trivial. We're looking across the whole addressable range for the program ROM. Now, depending on a particular bit of the control register, we're either operating in this pair of 16 kilobyte banks or a single 32 kilobyte bank. In the case of the latter, we just take our bank offset pointer, multiply it by 32 kilobytes and the offset provided by the write command in the first place to map it into our program vector. That's very simple. And as we saw with the previous mapper, splitting it into two 16 kilobyte chunks, well, each one of those chunks depends on the offset value stored in its corresponding variable here. PPU read acts in a very similar way. There is no RAM to worry about this time, but again, a bit in the control register is used to determine whether we're operating in this large chunk mode or a smaller chunk mode, and the offsets are calculated accordingly. As you'll find for many of the mappers, PPU write doesn't do very much. So the big and complicated and interesting function to look at is CPU write, because this is the function we'll use to program the mapper. We've already talked about the RAM access, but now we want to be sensitive to anything within the program memory range. And at all times, if the 8th bit of the data that is written, so doesn't matter what location as long as it's within that range, we reset our mapper's internals. This includes our bit counter. However, if that bit is not set, then we're sequentially and serially loading data into our load register. So it'll take 5 writes to fully populate this register, and each time we shift it along one and bring in the least significant bit of the data word. I'm going to increase our bit counter so I know that when I get to 5 bits, it's time to do something and change the state of the mapper. Recall that the address space was split into 4 distinct zones, corresponding to some internal register on the mapper. The first zone is used to directly set the control register. So we take the 5 bits of our load register and directly implant them into the control register. At this time, we can also choose the mirroring mode, which is software programmable, by analysing the bottom 2 bits of the control register. Setting the control register has now also set which operating mode our bank selection is using. Is it using the big chunky banks or is it using the smaller banks? The next zone, in inverted commas, was used for setting the low bank of the character ROM. And as usual, it depends on whether we're operating in 4K mode or 8K mode. The next zone was responsible for setting the high bank of the character ROM. If you're setting this specifically, you must be operating in 4K mode rather than 8K mode. The final zone configures the program ROM mapping, and the specifics of this mode can be determined by looking at 2 specific bits in the control register. In program mode 0 or 1, we're using the big 32 kilobyte bank select, and so we take the data from the load register, which will contain the bank number that we're interested in and apply it directly to our 32 kilobyte offset. This is where we slightly deviate from previous mappers in terms of where the fixed bank resides. In program mode 2, we fix the lower 16 kilobytes of our addressable program space to the first bank provided by the cartridge, and our upper 16 kilobytes of program memory is the flexible one that can be moved around, so we choose which specific bank that is from our load register. Program mode 3 behaves in a very similar way, but also opposite, that our lower 16 kilobytes is flexible and our upper 16 kilobytes is fixed to the very last bank provided by the cartridge. This is the one we've seen today in a previous mapper. Once we've finished with all 5 bits, we reset our load register and the load register counting variable. Ready for the next command. And that's it for Mapper 1. Once you get past this sequential loading idea, the actual implementation of the mapping is nothing more complicated than what we've seen on the simple mappers so far. Okay, time to talk about the last mapper I'm going to mention in this video, and that is Mapper 4, or MMC3 as its formal name. And this is a very important mapper to make because it's responsible for pretty much the other half of the games in the catalogue of games provided for the Nintendo console. In terms of complexity, this mapper is no more complex than Mapper 1, really. It has a little bit more sophistication in how it can do its mapping, and it's got some additional features. If we look at its capabilities, what we can see here is that the program ROM mapping can be split into 2 flexible 8 kilobyte chunks and 1 16 kilobyte fixed. Now, in my implementation, I found it convenient to think of it as just 4 8 kilobyte chunks mapped across the 32 kilobyte addressable range. The character ROM is mapped in a similar way. Here it is listed as 2 2 kilobyte chunks and 4 1 kilobyte chunks. However, I've decided to implement this as 8 1 kilobyte chunks. As with MMC1, the name table mirroring is software programmable. But we've also got this new addition, interrupt requests, and we'll look at that a little later. In terms of verbosity, the NESDev wiki article is an excellent resource here. And like all of the previous mappers, we write to the mapper by writing to any address 8000 or above, and depending on the address and the data, we set specific internal registers on the mapping chip. For this video, I'm really only going to detail the program ROM mapping because the character ROM mapping at this point is quite analogous. So I've split up my program memory into 4 8 kilobyte chunks. And the first thing to note is that the final 8 kilobyte chunk is always mapped to the last 8 kilobyte bank on the program ROM. Fortunately, this time round we don't need to concern ourselves with serialized behavior. We can write to specific addresses, and it turns out, just as before, there are 4 distinct zones which set specific registers, but each one of those zones is split into an odd and even, and the numbers are mirrored throughout the zone. The 4 functional zones can be split in the following way. This first region handles the mapping. This second region handles mirroring. And these bottom 2 regions handle information regarding IRQs, and we'll look at that after we've looked at the mapping. In this mapping zone, when even addresses are used, we're configuring the mapper with how to configure the mapper. Sounds a bit strange. And when we use odd addresses, we're actually providing the data for the actual mapping itself, so the addresses in the program ROM. So what do I really mean when we send these even addresses? Well, when we write a data byte to, let's say, address 8000, we're configuring the state of the mapper, but we're also preparing it for future data to come. So specifically, this bit is going to tell us something about how we're going to handle character mapping. And this bit, specifically how we're going to handle program mapping. These bottom 3 bits are used as an index into an 8-element array, which I'm just going to call register. And so subsequently, when we write with an odd address, the full 8-bit data is written into that specific register, given the index we've just received from a previous write to an even address. These 8 registers identify which bank in various ROMs do we want to use. Now, MMC3 is, from an implementation perspective, quite simple, but from a conceptual and how do you use it perspective, quite complicated, because the mappings tend to jump around a little bit. This is always the case. So really we're looking at how do we map these other three 8 kilobyte chunks. Well, if this bit is set, then this chunk is directly mapped to the second to last bank in our program ROM. And this chunk is directly mapped to whichever bank is identified in our array of registers, element number 6. Regardless of whether this bit up here is set, this chunk is mapped onto whichever bank is pointed by register number 7. If the bit is not set, then these two effectively swap around. This implements the fixed 16 kilobyte mapping, because this 16 kilobyte range here is always fixed to the last two banks, which is also 16 kilobytes, in the program ROM. And these two remain fully flexible. In a very similar tangle of spaghetti, the character mapping happens the same way. Here I've got the PPU address space broken up into 1 kilobyte chunks. If that bit in the data word is set, then this chunk uses the address of the bank in register 2, register 3, and if it's not set, we see that the registers are used in different places. So this one is now set by register 2, and so forth. Recall that in the mapping, 2 of these blocks are specified as 2 kilobytes, and 4 of them are specified as 1 kilobyte. Well, here we've specified the 1 kilobyte blocks, but we still use the same registers to get that information. Just so happens that these two will use register 0, and these two register 1. And the same applies on this side. But this, of course, implies that we're specifying 2 different locations in the PPU address space to the same bank in the ROM, which doesn't seem ideal. Well, the programmer will have anticipated this and knows that for here they need to specify 2 kilobyte banks. And so we can implement this mapping by taking the value in register 0 here and simply adding 1 to it before multiplying it by 1 kilobyte to work out where the offset is in the character ROM. This would of course assume that the programmer knows that the boundaries between these banks in the ROM need to be multiples of 2 kilobytes. But if they specified an odd bank number, this would lead to us having non-boundary aligned banks being accessed. So we can protect ourselves against that by simply ignoring the least significant bit. I don't know if that ever happens in reality, but it's a nice little safety check to put in. So what we see from this mapper is it's actually quite flexible in how you go about mapping the various ROMs to the addressable spaces of the CPU and the PPU. Yeah, it takes a little bit of thinking about, and perhaps they had automated tools which helped them. This leaves us with 2 remaining functions of the MMC3 mapper, and that is handling this new feature, interrupt requests. And I'll add that this isn't an interrupt request to the mapper to go and do something. This is the mapper generating an interrupt request for the CPU. And so far in this series, we've not really handled any interrupt requests, other than the non-maskable interrupt issued by the PPU. That particular interrupt was used to inform the CPU that it had finished rendering a frame, and therefore the game loop could go ahead and get the input, do some calculations, and produce the output for the next frame. In many games, it's useful to split your screen into different regions, particularly if you've got status bars. So for example, in this region up here, you could have score information, and perhaps down here you have inventory stuff. I don't know. Leaving this region in the middle to have some sort of game environment. And we looked in the past at the PPU how it handles split screen scrolling. And in games like Mario 1, as the scanline is zipping across the screen, it waits for a specific pixel to be hit, and that issues a sprite hit event to the CPU, where an on-screen sprite collides with a background sprite. And the CPU could use this to crudely measure whereabouts in the frame the rasterizer is up to, and use this information to change its rendering information accordingly. The problem is, per frame you only get to do this once. And given that the PPU is an entirely deterministic system, you would think it would be easy to synchronize the CPU and the PPU, but it isn't, because the CPU instructions are variable in length, so you can never guarantee where things are going to line up depending on what's happening within the game logic and what's happening on the screen, and various other factors, perhaps even controller input being pressed that frame, is changing the synchronization between the two processes. It also means that you're potentially sat waiting in a loop for an event to occur, and this is wasted processing time. A slightly more elegant solution would be to have some peripheral system actually count the scan lines for you. And when that count of scan lines hits a particular number you've programmed in advance, you can issue an interrupt to the CPU. And this provides a much cleaner and predictable solution. The only problem is there's nothing on the NES that will do this. There's nothing in the PPU that will do this. And so this functionality has been added to the mapper. And it does this in an exceptionally clever way, and this is a real testament to designers at the time that had to really try and squeeze everything out of the technology they had available. The only way the mapper can know about which scanline is being operated upon is by looking at the PPU address, because that will scroll through the various memories at various predictable stages during the rendering. And by keeping track of this address, it can detect when there has been a memory address change in such a way that would typically reflect the end of a scan line. Now, if you're really hardcore about making your emulators, you could go ahead and implement this logic and try and get it as cycle accurate as possible. I've not done that with my emulator, so it's not strictly an option for me, but because I have written this emulator, I can cheat. Therefore, I will add specifically to my mapper interface a function that is called when a scan line has been completed, and the mapper can accumulate these calls and issue an IRQ when required. Now let's have a look at my Mapper 4 implementation. I've now added some additional functions to the interface to handle the IRQ, and this is that scanline function I've just mentioned. Internally, I've got those 8 registers, and I've also created 2 internal arrays to store the bank offsets for the character and program ROMs. We also need some counters for our interrupts, and there's an interrupt counter reload value, so this is how many scan lines need to occur before the IRQ gets issued. And I've got some status flags to handle the IRQ internally. And as before, I've got some static RAM, a mirroring mode, and some mapper infrastructure. Those 2 bits that set the mapping tables accordingly, and the bottom 3 bits of the data word which indicate which register we're writing to on the next write. So let's look at CPU read first. As before, we handle the static RAM. Now, in the spirit of this series, I've deliberately kept things verbose, so I'm absolutely certain there are ways you can condense this into some nice numerical trick, but I didn't want to hide behind too many binary tricks, just so it remains visible what's going on. But when we're reading from the program memory, we can see which bank offset we've got in our array for a given range, and we just go and find that in the program ROM supplied by the cartridge. Very simple. In exactly the same way, PPU read looks at the range and chooses the corresponding bank from our array of bank offsets. There just happens to be quite a few of them, each one representing 1 kilobyte of character data. The reset function defaults the mapper to a known state, and by default it's in this fixed upper 16 kilobyte mode. So the last 2 chunks of program memory are mapped to the very last 2 banks of program ROM memory on the cartridge. Configuring the mapper, as always, is done in CPU write, and it's much simpler this time round because we actually have specific zones and all we're doing is checking if the address is odd or even. So in the first zone, which is configuring the mapper itself, arguably the most important one, we first check is it odd or even. If it's even, then we're configuring that target register and the 2 bits that control how we do the mapping later on. If it's odd, then we're updating 1 of the 8 internal registers. And then we just go and implement our tables directly. I'm not going to go through those, other than to say they just set the bank offsets in the program ROM according to how our internal array of registers has been programmed. The next zone was responsible for handling the mirroring, and in my emulator I'm only interested in even addresses being used here, and we specify the mirroring as being horizontal or vertical. The wiki article says there's also something to do with RAM protection, though I've not implemented that. The third zone down was handling the IRQ. If it's even, then we're setting the number of scan lines we want to occur before the IRQ fires. If it's odd, then we're just resetting that counter. And the final zone is used to enable the IRQ, allowing it to happen or not at all, regardless of the counter value. So all that's left to mention in this mapper is this scanline function. Every time it's called, it just decrements the counter, and when the counter reaches 0, it reloads it with the value that we've set, so we can get it to fire every 5 scan lines, every 20 scan lines, every 39 scan lines, whatever. In the event that the IRQ counter has equaled 0 and we're actually interested in receiving IRQs, we'll set this IRQ active variable to true. On the bus, in the clock function, which is where we do everything, I can check if the mapper is issuing an interrupt request. If it is, then I want to clear it from the mapper, but issue the interrupt request to the CPU, and the program will go and handle that accordingly. And finally, in the PPU itself, this is in the clock function for the PPU, we know when we've reached the condition of the end of a scanline. So I'm just going to call the scanline function of the mapper directly. This is my hack, so the mapper doesn't have to monitor the PPU addresses and make that decision for itself.
And so there you have it, a quick look at how I've implemented the mappers in my OLC NES emulator. I still don't claim that it's the most accurate emulator in the world, nor is it going to be the most compatible, and perhaps this discussion of mappers has provided evidence as to why that might be the case. There's a lot of mappers out there and a lot that we've not looked at. Anyway, I've posted all of the source code for these mappers on the GitHub repository. If you've enjoyed this video, a big thumbs up please, have a think about subscribing, and I'll see you next time. Take care.